Chapter 3, I frequently refer to as math and measurement. It's getting us into lab and talking about how we're going to measure, and then it's also looking at a lot of the math that we do and getting a regulated system. So what I'm going to do in this video is run through a lot of the terms that are related to measurement, and then in class we will actually be applying those terms. Okay. Our first term is accuracy versus precision. Be aware in science always that the definitions that you have for words and the scientific definition is not always the same. Precision, when talking about data, is how close your measurement is to other measurements you've taken. So if you measure the answer to be 5, it's the fact that you consistently get 5, those would be precise measurements. Okay? They're compared to one another. Accuracy, on the other hand, is not about being repeatable, it's about being right. So an accurate number is a number that's close to what the expected value is. If you expected to get 5 out and you get 5, that number is very accurate. Okay. Frequently we're looking at an average for accuracy, but you can look at just one single number also. If you look at the bullseyes on the screen then, just to run from left to right as we describe those points on the bullseye. If our goal in this case was to get the bullseye, target on the left shows data that is both accurate and precise. All of your data is grouped around the bullseye, which was your goal, so you're very accurate. And all of your data is grouped together, so they're very precise. Moving to the next one, if you look at those data points, if you took an average of those data points, you would probably be very close to the bullseye, meaning you're relatively accurate in this case. But you are not very precise because your measurements are all over. They're not grouped in one location. The next target, so the third from the left, you have all of your measurements grouped again, so you are very precise. You are always hitting the same location, but you are not very accurate because it is nowhere near the bullseye. And then the fourth one, the one all the way to the right, is essentially not accurate and not precise. Your average does not get anywhere near the bullseye, and your measurements aren't grouped. The term precision is also used in one other way. When we talk about precise measurements and precise measurement tools, what we're looking at is how well the number is measured or how well the number is known. Another way to say it is to what place value the number is measured. Let me give you an example. If you measure that your volume is 10 milliliters, and then with a different instrument, you're able to measure that your volume is 10.1 milliliters, the 10.1 is considered more precise. It's more well known. You know the number that's in the tenths location, where for the other one, you did not. If you then had another instrument that allowed you to measure the fact that it's 10.15, that's even more precise. It's even more well known. You now know to the hundredths how much volume you have. So your instruments that allow you to measure more places are considered more precise tools because you know your numbers better. When we measure things in the lab, we'll be using the SI system or the system International. It's our units, okay? The units that we'll use in science. If you have heard of the metric system, this is the same thing essentially. Okay? It's the modern form of the metric system. Why do we use it? We use it because it's easy. Okay? You are used to the imperial system or the English system where 12 inches equals 1 foot and 3 feet equals 1 yard and 16 ounces equals 1 pound. And I think you guys usually even know how many feet are in a mile, which is awesome. But if you notice there's no consistency. You have to know all the numbers to get the conversion right. And there's no relationship. The conversions that you use for distance are different than the conversions you would use for volume. And in that way, people don't like to use it in science. It's too much to memorize, surprisingly enough. So instead, we use the international system, the SI system, where all of your units have a relationship of base 10. And regardless of whether you're measuring mass or volume or distance, they all have the same base 10 relationship. So all you have to do is memorize what the prefixes are, and then you can relate it to any unit. Okay? So as long as you know your base unit and your prefix, sky's the limit in terms of your relationships. Here are the base units we will be using. You need to know what your measurements are in. Okay? When you do length in this class, you'll be using meter or centimeter. Mass is in kilograms or grams. Time is in seconds, sometimes minutes or hours, but usually seconds. Temperature is in Kelvin, and I'll talk about that in a second. It has a good relationship with Celsius. Your amount of substance is called a mole, and we will learn all about that conversion. The other two base units here, electric current and luminous intensity, we won't use in this course. You will use them in physics. We also have something called a derived unit. It's not a base unit, but they're units that we use a lot. The deal with a derived unit is that you don't have a measurement in lab to get a derived unit, meaning you can't walk into a lab and measure density. You can take a few measurements and calculate density, but you don't have a density tool, and that's why it's called the derived unit. Okay? So derived units we'll be using density a lot. We'll be using energy. We'll be using pressure, and we'll be using volume. It's crazy to see, but volume is on the derived units list. What's nice about volume is that over time we do have a measurement tool that does volume, right? We've got our graduated cylinder, but volume, the unit of volume, was originally related to length times width times height. Eventually the relationship that was established is that 1 centimeter cubed equals 1 milliliter, and milliliter then became our way of measuring volume for a liquid in a lab. But it came from the idea that if you take length times width times height of a centimeter cubed, you get 1 mil. Temperature, for our units for temperature, we'll be using Kelvin. Okay. The reason we use Kelvin is that because temperature has a relationship with energy. Okay. It's supposed to be a measure of your average kinetic energy in your system. If you remember, kinetic energy is motion energy, so really temperature is a measure of motion, how much and how fast things are moving. Think about the temperature scales we usually use, Celsius or Fahrenheit. It's kind of nonsense in relation to this definition, because at some point that you experience in your everyday life, you would hit 0. 0 would then mean no energy or motion, and we know that's not true because we get negative temperatures on the Celsius and Fahrenheit scale, which makes no sense in relation to this definition. The temperature is a measure of average kinetic energy. So what we measure in is Kelvin, because Kelvin is an actual scientific scale based on the idea that 0 means something. 0 is where nothing moves. So how do you calculate Kelvin? Well, what's funny about Kelvin is we don't have Kelvin scales in the lab, no Kelvin thermometers. So you measure in Celsius when you're in a lab, and then you convert. And the conversion is shown on the screen. Whatever you get for degrees Celsius, add the number 273 to it, and you get Kelvin. Memorize that number 273 because you'll be doing this a lot. Density, I already mentioned too, it's a derived unit. It's a physical property of matter. It's something that's very powerful to be able to calculate and measure. It's a measurement of how much stuff there is per space. Okay, stuff, again, is mass. Space is volume. So it's how much stuff there is mass per volume. Okay, how much mass there is per volume. It's something called an intensive property, which means it's unique to the material. Right? It's a physical property of the material. It will not change. Meaning if the density of liquid water is 1 gram per mil, which it is about, there's nothing you could do to affect that for liquid water. If you were trying to change the density, you would change the material. Okay? Add more, take away some, move it to a mountain. Liquid water is 1 gram per mil. That's an intensive property. unlike mass, volume, temperature, right? If you add more to mass, you change your mass. If you add more of something, you'll change your volume. If you heat it up, it gets hotter. Okay, density is independent of what variables you would affect. The equation for density is given here. D equals m divided by v, because it's how much stuff, which is mass, per how much volume, which is v. And because this is a derived unit, there are lots of varieties of what the unit might be. Okay, grams per milliliter is very common, especially for our lab, but it could be grams per liter, it could be kilograms per liter, it could be grams per centimeter cubed, it could be grams per meter cubed. There's lots of varieties. So you're just looking for some amount of matter per volume of matter. So how do you solve density problems? This is simply an equation where you'd plug it in and solve. Okay, so for this problem, there's 505 grams of sugar in a volume of 315 milliliter, and the question is, what's the density? Well, the density always equals mass per volume. So, since the mass is 505 grams, and the volume is 315 milliliters, all you do is take the top number divided by the bottom number, and in this case, you would then get the density to be 1.60 grams per ml. You'll learn soon what you should round all your numbers to, but this is the correct answer for this problem. For the next one, it's given that you have a density of 1.63 grams per milliliter, and the question is, what is the mass when you have a volume of 250 mils? So what is your mass when you have a 250 milliliter volume? You're going to rearrange these variables and isolate it so you have this question mark by itself. So if you take this 250 and move it up to the other side, you'll take 1.63 times 250 to get your mass. So you get a final answer of 407 grams equals your mass. The goal of doing this video like this is we'll have time in class to do a lot more practice and examples and make sure you can do a density calculation very simply. But I'm going to say right now, because I get a chance to, units. Every single number you write down in chemistry will have a unit from here on out.